Hi, welcome to our 19th lecture in Graduate Combinatorics. Today we'll start talking about graph theory. So graph theorists are quite proud to state that this field has started with the work of Euler. So the paper that they refer to is was written by Euler in 1736, or at least appeared in 1736, and it deals with Königsberg bridges. So in the town of Königsberg, you have a river Pregel, which is drawn there with blue ink. And you have 4 pieces of land. So you have a north part, then you have an island, it's called A, and then you have a south part, B, and this other piece of land here, D. You have 7 bridges connecting them, and the challenge that was posed to Euler was to go through every bridge exactly once and return to where you started. Now, Euler didn't actually construct a graph related to this problem, but he mentioned in his paper that this is a problem which involves geometry, but it's not a geometry of measurement, in the sense that it doesn't matter how deep the water, how long the bridges are, and what are the areas of the islands and so on. But it's what he called geometry of position, and he actually referred to Leibniz, to a work of Leibniz from 1679. Now it's believed that he was talking about geometry of position is the same thing as topology. What Euler meant basically that here it doesn't matter, all these measurements are not important. What it matters is how these entities, the land masses and the bridges are incident with each other. Now there is a very nice paper due to Brian Hopkins and Robin Wilson, which is called "The Truth About Königsberg," and it won a quite prestigious prize, Polya Award from the Mathematical Association, American Association in 2005. I posted it on the Google Drive, so you can read more about Euler and these bridges. Now, in our situation, we will model the problem using graphs, and I'll come back to basically explain the Euler's argument in terms of graphs in a little bit. But for now, so we will represent the 4 pieces of land by these dots. Here you have A, the south part B, this east part D, and the north part by C. And we will denote, give names to the bridges. Actually, in the paper of Hopkins and Wilson, actually they researched the names of these bridges. In our case, we'll just use A, B, C, D, E, F, and G. We have 7 bridges there. Okay, and the challenge is kind of like one of these puzzles that sometimes you give your friends, is to start at one of these dots and go through every connection, every segment or curve coming out of that dot exactly once and return to where you start. So we'll in this situation, so what Euler observed was that if such a route was possible, then that would mean that whenever you traverse a bridge, let's say you go on a bridge, you go to a piece of land, and then you have to come out from that piece of land, but you cannot use the bridge that you use in the previous step. So you have to come out on a different bridge. And in order for someone to go through, to start at some node, go through every bridge exactly once, and come back to where they started, the number of bridges incident with each mass land would have to be even, because every time you go through one of these pieces of land, you're using exactly 2 bridges connecting them, one to go in there and one to come out. But in our situation, that's not true. Actually, each piece of land has exactly an odd number of bridges coming out of it. So that that it's a proof by contradiction, showing that there is no way you can go through every bridge exactly once and come back to where you start. So we'll come back to this problem, and we'll discuss it and solve it in a more general setting, and we'll show that this condition about the number of bridges at each piece of land being even is actually necessary and sufficient for the existence of a circuit that goes through every bridge exactly once and returns to the starting point. But to do that, we need to introduce some notations and get more familiar with these notions of graph theory. So let's start doing that now. Now, the definition that I'll give here of a graph, it's perhaps may seem a little bit more complicated than what you think of a graph, which is essentially an abstract model of a network. But it deals with all possible generalization in terms of multiple edges or loops. So these are some kinds of edges that could appear in a graph. So let's just go through it. So a graph gamma consists of a set of vertices, which is usually denoted by V, and a set of edges, which is denoted by E. So for the picture on the left, V would be, the set would be A, B, C, D. And the set of edges E will be lowercase a, b, c, d, e, f, and g. Okay, so these are the objects. So of two kinds, a vertex and an edge. Now we also have a way of in which they're incident with each other, and this is given by a map, by a function, which associates to each edge an unordered pair of vertices. Let's call them x and y, which are called the endpoints of that edge h. So in our situation, if we were to describe this map explicitly, which will rarely happen, but we'll do it here just to make sure that we are comfortable with all the notations. So our function psi from the edge set, so I denote here by V choose 1. These are all the subsets of cardinality 1 of V, and V choose 2, all the subsets of cardinality 2. So psi of A, so if you look at A on the picture, you see that A goes between A and B, so those will be the endpoints. And so psi of A would be A and B in our case. But also it's the same thing that psi of B also equals this two subset A and B. Okay, and so on. So you can write them for all of them, but I think from the picture it's pretty clear what is happening. Now there are situations, so I'll jump to another example here. There are situations in which you can have a graph in which you have let me draw it by a picture. So let's say here, let's call this x, y, and z, and let me call this A, B, C, D, F, G, K, L, M, N, and P. So for this graph that I have at the bottom, the vertex set consists of you have 3 dots, so X, Y, and Z. Now the edge set consists of these connections between them, K, L, M, and P. And now what you see here is that the map that associates to the edge K, let me put it this way. So psi of K here consists of one vertex, so it's just the vertex X. So I won't write it as XX, but it's just this vertex X. And similarly as before, you can have that psi of L is the same thing as XY, and the two that are the same, psi of N will be the same as psi of p, and they will equal, each of them will equal yz. Okay, so this is a different example, and in this situation we have these maps. So for the edge k, its endpoints are equal, are basically x and x. So in that situation, psi is contained in the collection of one subset of the set of vertices. Now, these are special situations, and the edge like here, this edge k, this is an example of what is called a loop. So that's an edge whose endpoints are equal. And two edges, like in the case above, where you have A and B, so A and B, can call multiple edges. So the situation here is that you have two edges that have the same set of endpoints. So these are multiple edges, the same thing as here. You have multiple edges. I should delete this part. And so we have this situation here, and we have this situation here with N and B. So in its greatest generality, the definition of a graph, this is actually an undirected graph, so we don't care about the direction. So we're dealing with unordered pairs. So you could have the situation that an edge, to each edge, you can associate either two distinct endpoints, or it would be just one, two endpoints that are actually equal, in which case you get a loop. Okay. All right. Now, so that's the definition of a graph. When we when we don't want loops and we don't want multiple edges, that graph has a name. So a graph is called simple if it has no loops and no multiple edges. And in such case, we don't need to worry too much about the map psi. It's pretty much understood from a picture. So if I were to give you a graph like this, let's say this graph, and these vertices here are A, B, C, D, E, and F. So it's clear from the picture that, yeah, this is a vertex set, A, B, C, D, E, and F. And the edge set, it's clear that it consists of all these pairs for which I drew a curve between, or a segment between the endpoints, okay? So all of them, and so on. So in this case, we have seven edges, and I'm not going to list them. And the function psi, it's pretty much well understood from the picture. Okay. All right. Now, before we prove some results, let's look at this our example with the bridges. So this one, we have A, B, C, D, and then we have the edges A, B, C, D, E, and F and G. Okay. So let's look at this example, and we can interpret it in a different way. So let's look at it through as a matrix in which we see how the vertices. So let's write the vertices as rows. I have A, I have B, I have C, and I have D. And then let me write the edges as columns. So I can A, B, C, D, E, F, G. And now in this matrix, okay, so I have A there, B there, and C there. So what I will write when I look at the column of a matrix, I have a column is an edge A, and what are the vertices that are involved? What are the endpoints of A? They are A and B, and I'm just going to write the characteristic vector of that edge in the column. So I put a 1 here, and I put a 1 here, and I put a 0 and 0 here. And I will do the same thing for B, and B has the same endpoint, and I do the same thing for C. In this case, C is between A and D, so it's 1, 0, 0, 1. D is the same, has the same endpoint, so 1, 0, 0, 1. Then I have E. E goes between A and C, so I have 1, 0, 1, 0. And then I have last two, F. F goes between B and C, so there's a 0 here, 1, 1, and 0. And then G goes between C and D, so I have a 0, 0, 1, 1. Okay. Now what I wrote here, this is an example of an unordered or undirected incidence matrix of the graph gamma. And I will write it down. So this is before I write down the formal definition. So this is an example, and another way of keeping track about the the connections between these vertices and edges. And I can do the same thing here for this little graph that I have on the right, on the bottom left, because I have a loop. So I want to tell you how you deal with having a loop. So let me just erase here. Okay, so you remember we put the vertices as rows. So we have X, Y, Z, and then we have our edges, K, L, M, and P. Okay. And now here comes the difference. When we have a loop, the K has endpoints X and X, so we put here a 2 and we put a 0 everywhere else. L has endpoints X and Y, so we put a 1, and then we put a 0. M has X and Z, so it's 1, 0, 1. And N and P both have Y and Z, so 0, 1, 1, and 0, 1, 1. Okay, so this is the example of an incidence matrix in this situation. And yeah, so now let's give the formal definition of this matrix. So this is V times E matrix. Let's call it M, where for any X in V and for any H in E, the entry in the row X and in the column H is defined as follows. It's 2 if H is a loop containing X, 1 if H is a non-loop edge containing X, and 0 otherwise. Okay, so now it should be pretty clear that if I have the graph, like the picture on the left there, it's the same thing as knowing this incidence matrix. So it's just a different way of representing the structure of the graph. So actually in some data structures, sometimes you represent the graph in this way. You basically think of your edges as these 0, 1 vectors, you know, or 0, 1, or in this situation, having a 2 when you have a loop. But you can think of these edges as vectors. Okay. All right. So now what can we do with this? Well, we can prove our first result. And to do that, I need only one more definition. So given a graph gamma, vertex set, edge set E, the degree of a vertex X, is defined as the number of edges containing it, containing X, with the understanding that a loop, that any loop containing X contributes 2 to its degree. Yeah, I mean, this is a natural condition. If you think here, you see the edge K, is a loop at X. So by our definition, it's natural to, when we look at the degree of X, we add a 2 for the edge K, and then we add a 1 for each of the edges L and M. So the degree of X here is 4. Okay. And for the other ones is not such much of a discussion. The degree of each of Y and Z is 3 for each of them. Okay. So that's the degree. And the first proposition, this is called Handshakinglemma. And it states the following. So before I do that, the degree of a vertex X, I will denote it by D of X. Sometimes you will see it as deg of X, so on, same thing. Okay. So if gamma VE is a finite graph, so finite graph means that both the vertex set and the edge set are finite, then if we sum up all the degrees, summation over all X in V of D of X, we will get twice the number of edges, 2 times the cardinality of E. Okay. Now, how do we see? Well, in some sense, we already have a proof. If we look here at this, the picture that I drew here with this unordered, undirected incidence matrix of gamma, this is a matrix, like we said before, it has 0, 1s, and 2s in general. Now, if we look at each column, so the sum on each column, the sum of the entries is 2. This is because each column is an edge. And if the edge is a loop, then there will be 1 entry on that column that equals 2, and the rest of them are going to be 0. And if the edge is not a loop, there will be 2 entries on that column that are both 1, and the rest of them are going to be 0. So either way, the sum of the entries on each of these columns is 2. So if you add up all the column sums, the column sums are going to be 2 plus 2 plus 2. How many times? Well, 2 times the number of edges. Now, in a matrix, this is the same thing. When you add up the entries, you can do them in column by column. You can do them row by row. You can do them in any direction you like, zigzag if you want. But let's do it row by row now. So if you look at the row of A, what do you see in the row of A? Well, we are going to see a 1 whenever the edge, the corresponding column edge, is a non-loop edge that contains that that vertex A, or you will see a 2 if there is a loop for each loop that contain that vertex A, or you'll see a 0 if there is that column corresponds to an edge that doesn't contain A. In that case, when you sum up all the entries, you will get the degree of that vertex. So you get degree of A on the first row, which in this case is 5. Then you get the degree of B on the row of B, which is 3. And then you get the degree of C, and then you get the degree of D. So because of, the sum of the entries in this matrix have to be equal, it means that the sum of the degrees equals twice the number of edges. So if you want to write it formally, the proof is you say, we prove this result by, essentially what we did is a double counting. So double counting means summing up the entries of a matrix row by row and column by column. We count all the order pairs xh, where x is a vertex, h is an edge, and x is incident with h. So I didn't mention this word incident before, but in the definition here, a vertex is incident to an edge if that vertex is an endpoint of that edge. So let me put it here maybe. So it means that x is an endpoint of h. And now I'll just catch it here. The argument is before, if you do row by row, row by row, meaning we start with the first entry x first, then there will be dx such edges, and you have to summing up for over all x in V. And if you go column by column, which is the same thing as starting with h first, then this would be 2 for each column, and you have cardinality of A such many, that many columns. Okay, so this is handshaking lemma. It's usually the first result that everybody proves in graph theory, and it's very useful. Now it has various consequences, but the first one helps recognize sequences that could be the degree sequences of a graph. And to do that, to state the result, let me give you another definition. Given a graph gamma VE, a vertex X is called even if its degree d of x is even. And you have this corresponding definition. It's called odd if its degree is odd. Okay, so if you look at this picture, all the vertices here are odd because they have degrees 5, 3, 3. Here, I think x is even degree because it has degree 4, and y and z are odd because they have degree 3. Now, a consequence of handshaking lemma is the following corollary. It says that in any finite graph, the number of odd vertices is even. So here, for example, all 4 vertices are odd. So you have the number of odd vertices is 4, which is even. Here you have 2 odd vertices, y and z, so that's also even. So that's a property, it always happens that the number of vertices, odd vertices is even. So how does that follow? Well, let V0 be denote the set of odd vertices of gamma. Now, when we look, so from Handshakinglemma, implies that, so I'll just state it again, summation over all x in V, the degree of x, equals twice the number of edges, but this is an even number, so looking modulo 2, this is 0 mod 2, okay? But now, the sum of the degrees, so let's look at it again. This can be split in the sum of all x in V0, the ones that are odd, plus the sum of all the degrees, let's call them y, in V minus V0 dx that are even. This will still be congruent to 0 mod 2. But now, this part here, modulo 2 becomes 0 because every vertex here in V minus V0, we have the even vertices, and all of them are all such, so this should be dy, sorry. All of them are going to be congruent to 0 mod 2. So what we get is that the summation over x in V0 of dx is congruent to 0 mod 2. But each vertex here in V0 has dx odd. So this sum on the left-hand side is actually congruent to the summation over all x in V0 of 1. Because dx is congruent to 1 mod 2, but this is the same thing as cardinality of V0. So from here, we get that the cardinality of V0 is congruent to 0 mod 2. So that means that the number of odd vertices must be even. Okay. Okay. Now, so where I'm heading now is I would like to deal with the following question. If we are given a graph, so if we're given a graph, we can look at its the degrees of its vertices, and we can get a sequence of non-negative integers. Now backwards, the question is: if I give you a sequence of non-negative integers, is there a graph with that has that sequence as its degree sequence? So given set d1 greater or equal than d2, let's say greater or equal than dn, greater or equal to 0 of non-negative integers, is there a graph gamma VE with V equals, let's say, V1, blah, 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 Vn, and the degree of V1, of Vj equals dj for every j between 1 and n. Okay, so if that's the case, then if that is the case, the sequence d1 dn is called graphic. So that's a name, perhaps not the best name, but that's when you call that the sequence is graphic if there is a graph which has that degree sequence. Okay. One more thing I want to, before I discuss the variations on this problem, depending on what graph do you want to have. Let me give you one more definition. And this involves this notion of when can you tell that two graphs are the same. Now, I'm not going to give this definition for general graphs. I will just give it for in the simpler case of simple graphs. And so here's the definition. Let's say two simple graphs, say gamma, which has vertex set V and edge set E, and gamma prime, which has vertex set W and edge set F, are isomorphic. So it's just a fancy name of saying that they're the same if there exists a function, let's call it F, from the vertex set of one to the vertex set of the other, such that F is bijective, and the second property, so let's call it this A, and the second property is that xy is an edge in the graph gamma if and only if fx fy is an edge in the other graph gamma prime. So because of if and only if, what it means is that F maps edges to edges. So when I mean edges, edges in gamma to edges in gamma prime, and non-edges to non-edges. Okay. So that's a notion of being isomorphic. And in the case when gamma, so first, such F is called an isomorphism between gamma and gamma prime. Okay, I'll give you an example in just a second. So let's say we have a graph gamma here. Just draw it like this. I have 1, 2, 3, 4. And I have another graph over here, let's say gamma prime. Let me draw it this way. 1, 2, 3, 4. Okay. So the graphs look similar, but you know, how do you actually, in order to show that they're isomorphic, you have to come up with a function F from the vertex set of gamma, which is, I mean, in this case, I took both vertex sets to be the same. So this is 1, 2, 3, 4. To the vertex set of gamma prime, which is 1, 2, 3, 4. If you can put a prime here if it makes it easier to distinguish them, but it's not necessary. So it works for any labeling. So now you have to come up, what function is a bijection? I mean, they're 4 factorial, so there could be 24 such functions, but you want to map edges to edges and non-edges to non-edges. So here, if you look at the two graphs, they're both this path on 4 vertices. And so if you look at this vertex 1, because it has only one neighbor, it's kind of intuitively obvious that you should send it, it should be mapped to a vertex of degree 1 in the other graph. So there are 2 choices. You can map it to 2 or 3. So let's just map 1 to 2. And then in that situation, where do we want to send 4? This is the other vertex of degree 1. Then it makes sense to send, you have to send it there. So you send 4 to 3. And then what happens in between them, the neighbor, so 1 was mapped to 2, 1 is adjacent to 2, so 2 is adjacent to 4, so we should map 2 to 4, and then 3 gets mapped to 1. And you can actually check for each edge. So if you look at 1, 2 is an edge in the gamma, and the corresponding, under the image of F, that in gamma prime, that becomes what? 1 gets mapped to 2, and 2 gets mapped to 4. So that's the 2, 4, which is an edge. We see it here. And you can do the same thing for the others. 2, 3, under this map F in gamma prime, that becomes 4, 1, which is here. And the last one is 3, 4. 3, 4 gets mapped to 1, 3. So this is isomorphism. Now, when the graphs gamma and gamma prime are the same, and and you have this function f with this property, any isomorphism from gamma to gamma prime, so from gamma to itself, is called an automorphism of gamma. Okay, an automorphism of gamma, informally speaking, it's a permutation of the vertices that preserves edges and non-edges. So automorphism it's a bijection or permutation of the vertex set that preserves edges and non-edges. And if you take all the automorphisms and you put them together, that gives you a group. So automorphism of gamma is the set of all automorphisms of this graph gamma. And this is a collection of permutations, and it's not hard to prove that if you take two automorphisms and you compose them, they also, the composition is also an automorphism. And so automorphism of gamma is a subgroup of the symmetric group on V elements. And it's a measure of how symmetric your graph is. So informally speaking, the larger the automorphism, the more symmetric the graph looks like, the more the vertices resemble each other. And it will always be non-empty because the identity permutation is always contained in every automorphism. Is contained in every automorphism group. Now, so here's some other examples for which I'll leave you figure out the automorphism. If I give you the graph gamma like this, let's say 1, 2, 3, 4, 5, and I have gamma prime, this graph, let me label it the same way. Can you write down an isomorphism from gamma to gamma prime? So this is 5 here. So isomorphism, sorry. Can you find out an isomorphism from gamma to gamma prime? And again, the intuition for two graphs being isomorphic is that one is obtained from the other by relabeling the vertex set, essentially. In this case, it's not too hard. There are harder questions. So if you want a more challenging question, this is the Peterson graph, which is drawn this way. And you can label the vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you can draw Peterson maybe or other graphs in different ways. So you draw it this way. This one goes this way. And let's go this way. So you can label this here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So question for you, are these graphs, this is gamma and this is gamma prime, are gamma and gamma prime isomorphic? So to prove that they're isomorphic, you have to figure out an isomorphism. To show that they're not isomorphic, that's an interesting problem as well. In that case, you have to come up with some graph invariant that has different values for these graphs, for these two graphs, gamma and gamma prime. So I'll write it here, this observation that most graph properties or invariants are, well, not invariants because I'm using invariant now, graph properties or parameters are invariant and the graph isomorphism. So to give you an example, if gamma and gamma prime are isomorphic, then they have the same degree sequence. And that's not too difficult to see, is because if you have the graph gamma here and you have gamma prime here, this has v1 blah 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 vn, and this has, let's say, w1 wn, and let's say, you know, we have an f of vj goes to vj for any j between 1 and n. Then what happens is, well, vj has some neighbors here, x, y, z. Well, because vj has neighbor x, it means that on this, you know, because vj is f of vj, here in the, so this is in gamma prime, wj will be adjacent to f of x, and will also be adjacent to f of y, and it will also be adjacent to f of z, and all these values will be distinct because f is a permutation. So that means that the degree of vj will be the same thing as the degree of vj in gamma, but it's understood, will be the same thing as the degree of wj in gamma prime. Okay, but now the converse is not true. So there exist graphs gamma and gamma prime with the same degree sequence, such that gamma and gamma prime are not isomorphic. So the simplest example would be that I think of, let me take here gamma as being two triangles, and gamma prime, the hexagon. So these two graphs have the same degree sequence. All the vertices in gamma, you have 6 vertices, each of degree 2, 6 vertices, each of degree 2 in gamma prime. But these two graphs are not isomorphic, and you can prove that. You know, the one on gamma, we haven't discussed it yet, but gamma is not connected, whereas gamma prime is connected. So I will stop here for today, and in the next lecture, we will discuss the answer to this question here. Given a set of non-negative integers, when can we find a graph with that sequence of non-negative integers as its degree sequence.